All right, good morning, everybody. So the topic of today's lecture is equals part 2. And so in the previous lecture, we implemented equals using this get class method. I'm going to show you how to implement equals a different way. It's very similar to the way we did it in the previous lecture. There's only a couple of changes, and the changes won't seem especially important to you at this moment. They'll become important later on in the course. So in a couple of weeks, I think. So after reading week, we'll be talking about inheritance, and then you'll realize, then hopefully you'll realize that instance of is important in this particular case. Right? And so the version of equals we talked about in the last lecture is perfectly adequate if you're never using your class as part of what's called an inheritance hierarchy. And again, we're going to talk about inheritance in a couple of weeks. Now, if you are in an inheritance hierarchy, then you should consider using the version of equals that I'm going to show you. So this is, the reference for this is from this book, Effective Java by Joshua Block. All right, so it still has the same requirements, right? So an instance is equal to itself, right? So x equals x is always true, right? X equals null is always false. It's step 3 that changes, or requirement number 3 that changes. So in the previous lecture, we said that only objects with the exact same type can be equal. Today, we're going to let objects with compatible types be equal. So the compatible part will come again in a couple of weeks when we talk about inheritance. Step 4 is exactly the same. So if you get past step 3, everything is the same as what we talked about in the previous lecture. Right? So instance is always equal to itself, right? And so that's the same, right? You just check if this is equal to obj. Right? And if that's the case, you return true because you're comparing the same object to itself. All right, so the next requirement number 2 is that x equals null is always false. So in the previous version of equals, we had to explicitly check for this. Unlike the previous lecture today, we don't need to check for this because step 3 is going to, or requirement number 3 is going to test it for us. Right? And so instances with compatible types can be equal. And so we're going to use this thing called instance of instead of get class. So instance of, even though it's all spelled out like a big word or a pair of words, is actually an operator in Java. So if you have a reference and you write instance of and then some type, that returns true or false depending on whether reference, depending on how reference is related to that type there. Right? So you're going to write something like if x instance of 0.2, for example. So instance of tests if a reference refers to an object that implements a specified interface, right? So if you had an array list, t, and you wrote t instance of list, that would be true, right? So t is a list. Right? It also tests if an instance has the specified type here, right? So if you wrote obj instance of 0.2, that would return true if obj was a 0.2 object. It also tests if an instance is if reference is an instance of a subclass of this type here, right? And so that comes when we talk about inheritance. And in all cases, if that thing is null, then null instance of anything is always false. So you never have to actually explicitly test for null if you're using instance of. Right? So the instance of test gets us, oh, sorry, that's a bug. obj. So the instance of test handles the case where obj is null for us. Right, so we're going to ask, is obj a 0.2 object? And if it's not, we're going to return false. Right, and now we're back into the exact same situation as we were in the previous lecture. Once you get this past this point here, you know that obj is a 0.2 object. So you can cast obj to a 0.2 object, like that. Right, and then you can compare its x and y coordinates, again, using that somewhat convoluted recipe from the previous lecture. So this using double to long bits. So just remember that takes that double value and interprets the bits of that double value as though it were a long value. So this safely converts a double value to a long. And now we compare their integer, these two integer values here to determine whether or not the x coordinates are the same. You do the same thing for the y coordinates. If both the x and y coordinates of the 2 points are the same, we can return true, and we're done. Right, so that's the second version of equals. You can use either one in this course. It doesn't, unless you're in an inheritance hierarchy, you can use either one in this course. It doesn't matter. Right? If you're in an inheritance hierarchy, then you have to use the second version. And we'll look at that in greater detail in a couple of weeks. Right? So just keep that in mind, and we'll come back to that in a little bit. All right, so when you implement equals using Eclipse, which I don't have open, sorry. So when you implement equals using Eclipse, you can't just implement equals. Eclipse forces you to also implement hashCode. And so the question is why do you have to do this? Right? And the answer is because you must do this. Right? And so the rule in Java is if you override equals, you have to override hashCode. If you don't, then all of the hash containers will not work the way you expect them to. Right? So hashset won't work the way you expect them to, and hashmap won't work the way you expect it to. Right? Any other hash container won't work the way you expect it to. Right? So we're going to make a point P. Right? Its coordinates are 1 and -2. Right? We've overridden equals now. So if I make another point here, Q, whose coordinates are also 1 and -2, right? Then we know that P and Q are going to be equal. Right? If you take P and put it into a hash set or a hash map, it doesn't matter which, right? And ask the set, in this case, does it contain the point P? You get back the answer true, which is good. We just put it in, right? So H add P and then does it contain P? Right? That had better be true. The problem is if you add Q, if you ask the hash set, do you contain the point Q? Right? Now you get back the answer false. Which is confusing, right? P and Q are equal, right? The hash set ought to contain the point Q, right? Because you're kind of expecting the hash set to search itself to look for a point that's equal to that thing there, right? Unfortunately, that's not what happens. Sorry, that's exactly what happens. The problem is we haven't overridden hashCode, right? Okay, so what's going on here? Suppose you have a list of unique .2 points, right? So I've got a bunch of points in a list. I would like to know, does that list contain a specified point, right? So how would you do it? Well, if you had a list, you could just use contains. But if you didn't know about contains, you would just write a loop, right? So I'd like to know, does this list contain that point P? Right? So all you're going to do is you're going to write a little loop. Right? So here we're going to write a little for each loop. So for each point in my list points, right? If that point equals P, we know that the list contains the point P, so we can return true. Right? So the key here is that you're going to use equals. Right? That's the important part here. Right? If you search the entire list and you don't find a point that's equal to the thing you're looking for, you can return false. Right? Okay, so when you do that sort of thing, that's linear search, right? So you're going to search an entire list for something that you're looking for. If you double the length of the list or the array, that doubles the amount of time that or doubles the amount of searching that you have to do. Right? So in the best case, if there's n elements in the list, if you're lucky, you find the element in the first you find the element in the first location in the list, right? And so there's one called the equals. Right? In the worst case, you have to look at every element in the list, so that's n calls the equals, right? And on average, assuming the thing is in the list somewhere, it's going to be in the middle roughly, right? So that's going to be something like n over 2 calls to equals, right? Both the average case and worst case are in big O of n complexity. Right. Okay, so I'm pretty sure you know what a hash table is. Hash tables are collections that work in a completely different way compared to lists, right? And so in a hash table, just to quickly remind you how this works, you can think of the hash table as being organized into buckets. Right? So it's just a big array. You've got, in this case, n plus 1 buckets. Unlike an array, you can put more than one thing in each bucket. Right? So the way that Java implements this is that it says if you want to put an object A into this hash table here, right? The hash table, so your data structure calls this hashCode method that belongs to your object A. So hashCode is defined in the class big O object. And that means every object in Java has a hashCode method. Right? hashCode essentially turns the fields of an object into an integer. Right? So basically it maps an object to an integer value. The integer value can be any value, so it can be any integer. So between integer min value and integer max value, so it can be negative. When the hash table gets that number, it does something to that number so that it maps that number back into the range 0 to n minus 1, 0 to n. Right? Exactly how it does this depends on the hash table implementation. Right? But it takes an int and then converts it to the range 0 to n. Right? So that's what the red arrow means. Right? It doesn't mean the hash code returns 2. It just means that whatever the hash code value happens to be, it gets mapped to the number 2. Right? Okay, and so given that number 2, that's where the hash table decides to put the object A. Right? So to insert that object, it now puts A into bucket number 2. Right? If you insert another object into the hash table, right, it calls hashCode on that object, which returns some integer value. The hash table takes that value, maps it to the number 0 in this case, so it puts B in bucket 0. Right? For C, the hashCode for C gets mapped to n, so that gets put into bucket n. I think there's one more. Yeah, so D. So there's a second object, a fourth object, D. And in this case, its hash code value also maps to the number n. It doesn't mean that D and C are equal. It just means that when you compute the hash code using D and C, that value ends up getting mapped to n. So it now goes into bucket, into the last bucket of the hash table. Okay, so in a hash table, ideally the distribution of the elements is uniform, right? So roughly each bucket contains roughly the same number of elements, right? That's the goal. If you want to search a hash table, you just repeat the process, right? So if I want to look for the object equal to A, right, I just call hashCode on that on the object, right? That returns the number 2, so we look in bucket 2 and test every object to see if it's equal to A. Right? So is A equal to A? The answer is yes, right? So that returns true. So A is in the hash table. Right? What about Z? So when we search for object Z, the hash table asks for its hash code, right? Maps that value to the number n, and it now goes to the last bucket and just compares all the elements in that bucket. Right? Is Z equal to C? The answer is no. Right? Is Z equals to D? The answer is no. Right? Therefore, Z is not in the hash table. So searching one of these things is much faster than linear search. Right? It turns out that in a well-designed hash table, searching a hash table is in O1 time, right? So constant time. Now in the worst case, so if you have a badly designed hash table, or if you have a bad hashCode method, all of the elements end up in the same bucket. Right? And now when you search the hash table for the element, you have to search all the elements in one bucket, which is exactly the same as searching a list. Right? So in the worst case, all n elements are in the same bucket, and that leads to n calls to equals. Right? But assuming you don't have a assuming your hash table is implemented in a decent way, and assuming whoever implemented hashCode for your type did it in a decent way, the hash tables typically are very fast. Right? So typically it's O1 average time. All right, so all of this relies on you implementing hashCode though. Right? So if you implement a class and you override equals, you now have to replace hashCode. The reason why is because if you don't, you get the object version of hashCode. Right? And the object version of hashCode uses the memory address of the object as its hashCode. Right? So here, right, P is a new point object, Q is a new point object. Right? Because they're different objects, they have different memory locations. Right? That means when the hash table uses P to call its hashCode method, right, that's going to return a different value than when the hash table uses Q to call its hashCode method. Right? Different memory address, almost certainly different hashcodes. Right? So P and Q are different objects, therefore they have different memory locations. Right? Therefore their hashcodes are different, probably. It's not guaranteed. Right? So hashCode returns an int, right? So there's 2 to the 32 possible hashcodes. How many memory addresses are there? There's 2 to the how many possible memory addresses? Oh, so The virtual machine can probably only map 2 to the 64 different memory addresses, right? But there's many more memory addresses than there are unique hash codes, right? So there's no guarantee that the hash codes are different here, but they almost certainly are, right? And so that means the hash table almost certainly looks in the wrong bucket, right? And it doesn't find the object, forget complex number, this is a copy and paste error, right? So it doesn't find the object even though P equals Q is true. Right? So what do you have to do? Well, you have to replace hash code, right? So in our point2 class, we've implemented equals so that 2 points are equal if they have the same coordinates, right? Now when you implement hash code, you've got to use the x and the y coordinates of the 2 objects to compute the hash code, right? And so generating a hash code is difficult. So generating a good hash code is difficult. No one actually knows how to do it. No one knows how to generate a hash code for every possible object in a decent way. There is a recipe that seems to produce decent results in practice. If you want to know what the recipe is, you can look in the notebook for it. You don't have to memorize this, right? So don't memorize this thing here, right? So the basic idea, though, is that you want to take the fields of your object, you want to mash them together somehow and get an int back. Right? It would be nice if you had 2 objects that are not equal, that they also produced different hash codes, but that's not possible, right? And it's not required, right? So you can have 2 objects, 2 unequal objects that have the same hash code, right? So that's okay. What is required is that if the objects are equal, then their hash codes are also equal, right? And so that's so that the hash containers can actually find the object when they go to look for it, right? If they have different hash codes, then your hash table looks in a different bucket for the 2 objects, and it never finds the object, even though they're equal to one another, right? Furthermore, hash code can't be random, so you can't have any sort of randomness in your hash code method, right? It has to be it always has to return the same value as long as the object never changes its state, right? So that hash code method satisfies the requirement for hash code, right? So we can override hash code. So hash code always looks like public. It always its access modifier is always public. It always returns an int. Its name is always hash and then big C code, right? All that's required is that this return an int. So given a point2 object, you can just return 1 every time, right? If you do this, your hash set and hash maps become, the performance becomes very bad, right? This puts every point2 object into the same bucket, right? Your hash table is effectively a list, right? So don't do that. Okay, so what should you do? So my x and y coordinates, there should be double. There should also be private, but never mind, right? So these should be double values. So I need to somehow coerce them into being an int of some type. So you might say, well, I can just add them together and then cast it to an int, right? This is also a bad idea, right? Similar points end up having the same hash code and you end up in the same problem, right? So imagine you have an application where all of your points happen to be, their coordinates happen to be in the unit square, right? So in other words, their x and y coordinates are between 0 and 1. Right? This turns out to be more common than you think. So in a lot of science and engineering applications, we normalize all of the data, right? So that puts all of our values between 0 and 1, right? If you happen to be doing this for points, right? When you add x and y, if all your values are between 0 and 1, now all your values are between 0 and 2. So your possible hash codes are 0, 1, and 2, right? And this is going to cause most of your points to end up, all of your points to end up in one of 3 buckets. So that's no good either. Sorry, this is going to be 0 or 1. This can, well, I guess if x and y are exactly equal to 1, it can be 2. So 0, 1, or 2. So this forces all of your points into one of 3 buckets, which is also not good. Right? So what should you do? So it turns out that you have to override hash code every time you implement equals. So the standard library provides you with a method to actually produce a hash code using this method called hash. So it's inside the utility class called objects with an S, right? The method is called hash. You can pass in as many values as you want, and it will use those values to compute a hash code. Right, so that's the way you should do this in this course if you're asked to do this. Eclipse will also generate hash code for you. It doesn't, newer versions of Eclipse might do this, but I don't think they do. So the newer versions of Eclipse use, they will actually spit out a bunch of code for you that is essentially equivalent to using objects.hash. But the code it spits out is much longer. So if you look at the code that it, So if you look at the code that it produces, it ends up multiplying your fields by an integer, by a prime number, and then adding it to itself in some convoluted way. So this actually produces a reasonably good hash code. It's not a cryptographically secure hash code, so it's not a perfect hash code, but no one knows how to do that anyway. Notice the advice here is that writing such hash functions is a research topic best left to mathematicians and theoretical computer scientists. So all that's required is that you implement a hash code method that seems to work most of the time, right? Okay, so there's something you must not do, right? So that hash code method here is fine for our point 2 class. There's a lot of mistakes on these slides. There's no X here. All right, so anyway, remember that equals for point 2 uses the fields X and Y to compute equality, right? So when you compute your hash code, you can also use the fields X and Y to compute the hash code, right? You can use a subset of the fields that equals uses, right? So you could just use the X coordinate, or you could just use the Y coordinate, right? But what you can't do is you can't use more fields than equals is using, right, to compute the hash code, right? If you use more fields than equals uses to compute equality, right, then the requirement back here, right, if two objects are equal, then their hash codes are equal, will no longer be true, right? So imagine you've got 3 fields in your class. Equals is using 2 of them to determine equality, and you accidentally use all 3 to compute the hash code. Right? That now breaks that requirement there, right? Because that third field that you're using isn't being considered by equals, right? And so that's going to cause your hash codes to be different for 2 objects that are equal. Right? So you must use the same number or fewer fields that you use in equals than you're using in hashCode. To compute the hash code, you must use the same number or fewer fields than you used in equals. Right? So that's the one thing that you have to watch out for. Right? And that's why when you implement equals in Eclipse, it asks you which fields are you using to determine equality. And then it uses the exact same fields to compute the hash code. Okay, so that's all we need to say about hashCode. Right, so you've now got 3 methods that have come from object that we've now replaced. Right, so we've got toString, gives you the string representation of an object. Right, we've got equals, determines if 2 objects are equal, and now you've got hashCode. Right, return a hashCode for an object. Right, all 3 of those methods come from the class big O object. Right, which means you can replace all 3 of these methods in any one of your classes. Right, you're often going to replace equals, which means you're going to replace hashCode. Right, it's also extremely common to replace toString because it's useful to print out objects. And so it's very common that you replace all 3 of these methods in one of your classes. All right, so there's something else you often want to do. Now, this method does not come from equals. Right? So this method here is not one of the methods that belong to every object. Right? Compare to is the method that you want to use if you want to compare objects for order. Right? So in other words, it's the analog to less than, equal to, and greater than for objects. Right? So many objects have a natural ordering. Right? So dates you can sort by their time. Right? Short, integer, float, double, those are all objects, right? You can sort them by their values. Right? Strings you can sort by their dictionary order. Right? Dates can be sorted in chronological order. Now for points, it's not clear how you want to sort points, or even if you want to sort points. Right? You could, though, do something like compare points by their distance from the origin, right? So a point that's further from the origin is greater than a point that's closer to the origin, right? You could also do things like sort them by their x-coordinate or sort them by their y-coordinate, right? All of these are useful in certain circumstances. So if the class that you're implementing has some kind of natural ordering, then you should consider implementing what's called the comparable interface. So this is the first interface that we're actually seeing and using in the course. Right? If you implement comparable, then you can sort your array or your lists, you can sort arrays of your objects, lists of your objects. You can put them into a tree set or a tree map without doing any extra work. Right? And so this turns out to be very useful. Right? So what's an interface? So an interface is just a group of related methods that have no implementation. Right? So the comparable interface has exactly one method. Right? That is the complete comparable interface. Right? It's got this funny bracket notation here again. So this just indicates that it's a generic interface. Right? So if you're going to use this thing, you have to specify the type. So the type of value that you're comparing. Right? The interface says that there's a method called compareTo, right? And it takes in an object of type t, right? Whatever type you are comparing. And it returns an int. Right? So any class that implements comparable has to provide a compareTo method that looks like that. Right? So it must return an int. It's called compareTo with a big T, and it has one parameter. Right? What does this thing do? It returns a negative integer, 0, or positive integer if this object is less than, equal to, or greater than the other object. Right? So x dot compared to y returns -1 if returns a negative value if x is less than y. Right? It returns a positive value if x is greater than y. And it returns 0 if x is quote unquote equals to y. But that doesn't mean the same thing. It does not necessarily mean the same thing as the equals method, which is confusing. Right. Okay, so if you write x dot compared to y and y can't be compared to x, you get an exception. So that's the expected behavior. You don't have to test for this. This just happens. Okay, so suppose you want to compare points by their distance to the origin. So you decided, okay, so my points will be comparable by how far they are from the origin. So we're going to go ahead and implement the compareTo method. Right? So for point 2, the type here is point 2. Right? I can compare one point 2 object to another point 2 object. Right? So someone's going to write something like x dot compare to y. So the idea here is you compute the distance from the origin for this point, right? So x. You compute the distance from the origin for the other point, in this case y, and then you compare the two distances. Right? You return a positive distance if this point is farther from the origin. You return a negative integer if this point is closer to the origin, and you return 0 if the 2 points are equidistant from the origin. Right? So it's pretty straightforward to implement. So to your class, you have to do a little bit of surgery. You have to now say you're implementing this interface. Right? You can't just stick in the method. That doesn't work. Right? So if you try to put in @override and then public int compareTo, blah, 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 right? The compiler will flag that as an error. Right? It'll say there is no compareTo method in the type big O object. Right? So you have to tell it that you are, in fact, implementing this interface. Right? The comparable interface has this method, so you can override or replace the definition of compareTo that you got from this interface here. Right. The angled brackets in the point 2, that should be there as well. Right? So that name is usually the same as that name. Right? And now you just go ahead and implement that little algorithm over here. Right? So compare the distance of this point to the origin. So you could write this x squared plus this y squared, take the square root, right? Because that's the distance. The better way to do that is to use this method called hypot from the math class. Right? Hypot also exists in the C standard library. Right? So what hypot does is it computes the value that's equivalent to x squared plus y squared square root, but the way it computes it avoids overflow. Sorry, it doesn't avoid overflow. It avoids saturation, right? So if the sum x squared plus y squared take the square root is actually less than double infinity, hipot will calculate that value correctly. Right? If you compute x squared plus y squared, that sum can become positive infinity. And so when you take the square root, it also becomes positive infinity. Right? And so hipot is the correct way to compute the distance here. Right? It avoids all the issues with saturation. So that's the distance of this point from the origin. The distance of the other point from the origin, well, you just pass in other x and other y for the distance for the other point. And now you just compare the two distances. Right? So if this distance is greater than the other distance, we have to return a positive integer. It doesn't matter which positive integer. It's only the sign that matters. Right? So you can return 1. If the distance of this point is less than the distance of the other point, you have to return a negative integer. It doesn't matter which one. Right? So we can return -1. Right? If the distances are the same, we can return 0. Right? And it's better, so instead of writing the if statement yourself, you should rely on the standard library to do this for you. Right? So the class double knows how to compare double values. Right? And that's exactly what we're doing here. Right? So in double, there's a method called compare. So this is the double, oh, this is much bigger than I thought it was. So there's the double class there. If you scroll through its methods, right, you'll see that double has a compare to method, right? So you can compare two double values for their order. And it also has a compare method, right? So compare is static, so we're going to call it with the name double, right? Compares D1 and D2 for their values, right? And it tells you it returns the exact same value that would have returned, right? So as if you had called compare to on the two values, right? Which means it does exactly what we're looking for, right? So instead of writing that if statement yourself, just call compare and compare this distance to the other distance. It will return an appropriate int for you, right? And that's much easier to write. All right, so there's something funny about our compare to method, right? So remember what I told you earlier, compare to is the object analog of less than, greater than, and quote unquote equal to, right? So it returns 0 if this point is quote unquote equal to the other point, right? Notice when this method returns 0, right? It returns 0 if the points have the same distance from the origin, right? It doesn't return 0 if the points are actually equal, right? It's only using the distances to compare. Right? So all the points on a circle have the same distance to the origin. None of those points are equal to one another, but compare to says that they are quote unquote equal. Right? So you have to be careful that compare to doesn't necessarily mean equality. Right? It just means that however you're comparing them, the value that you're comparing happens to be equal. Right? Okay, so there is if you look at the documentation for compare to, so if you go and look at the comparable interface, you'll see that it has, again, just like equals, it has a very mathematical specification, right? And this is to ensure that compare to is imposing a natural ordering on your objects, right? The details of the contract don't matter, right, for our purposes. What's important, sorry, not what's important. What's important is that you return the sign, the value with the correct sign. Okay, so with regards to what's going on with equals, compare to is said to be consistent with equals. If x compared to y returns 0, then x equals y is also true, right? And if x equals y returns true, then x compared to y also returns 0, right? So this is, compare to is consistent with equals if and only if, right? Compare to returns 0 when x equals y is true. It's not required that this be the case, right? So your compare to method does not need to be consistent with equals. Right? So compare to can return 0, but your objects are not equal, right? And similarly, your objects may not be equal, your objects are equal, but compare to may return a non-zero value, right? And our compare to method for point 2 does exactly that, right? So for many points, x compared to y will return 0, right? Even though they are not equals according to the equals method. Right, so go back again here. Whoops, here, right? So 2 points are, compare to thinks that 2 points are equal if they have the same distance from the origin, right? Rather than do they have the same coordinates. So our compare to method for point 2 is not consistent with equals. Right? So that's the first case. It's harder to come up with situations for the second case, right? But it is possible to do. Okay, so if you're implementing compare to, when you get to the point where you're actually going to compare the two values, right, use one of the methods from float or double, right? So use float compare or double compare or integer compare or long compare, et cetera, et cetera, et cetera, right? Those methods will do the if statement for you. You don't have to write it out yourself, right? You can break this rule if you decide that compare to should return some sort of information, which we'll look at in just a second. Right? When you're implementing compare to, if your implementation is broken somehow, right? So if it's buggy, then any class or method that relies on compare to now starts to behave funny, in a funny way. Right? So tree set and tree map, those are the collections that sort their elements somehow. Right? How do they sort the elements? They call compare to on the elements. Right? So if your compare to is buggy, the tree set and tree map now appear to be buggy. Right? Arrays has a method in it that will binary search an array. Right? How does it compare the elements in the array? It uses compare to. Right? Collections has methods that will sort a list. How does it compare elements in the list? It uses compare to. Right? And so compare to is important, right? But remember, it doesn't come from object, right? It's its own, it belongs to an interface. So not every object has a compare to method. Right? All right, so every once in a while, you'll come across a compare to method that actually returns some useful information. Right? Point 2, there's no sensible information that you can encode in the integer value that's returned. Right? But the counter class, there is an example of a class that can return some useful information in its compare to method. Right? So you can compare two counters by their value. Right? So if you compare two counters by your value, a useful piece of information to know is what is the difference between the two counters. Right? And you can encode that difference in the return value of compare to. Right? So the value of this counter minus the value of other counter, right? That satisfies the contract of compare to, right? If this counter has a larger value than the other counter, then that returns a positive value, right? If this counter has a smaller value than the other counter, it returns a negative value, right? If the values are the same, then this returns 0. So this is perfect, right? This actually encodes some useful information. You have to be very careful when you write that, though, right? You are performing arithmetic here with some integer values. So that thing there might overflow, right? The only reason this is safe in the counter class is because you know for certain that will never overflow, right? This can't overflow because counter has a class invariant, right? It has an invariant that says its value is never negative, right? So you can never subtract a large negative value in this difference here. So that will never overflow. Right? But this is only true because the counter class has that invariant. Right? You can't write that in general. Right? If you write this in general, then that can possibly overflow, and now you've got a buggy compare to method. Right? The string class is another example of a class whose compare to method returns some useful information. Right? So the compare to method tells you the difference in the first character that differs in two strings if you compare them using compare to. Oh, okay. What time do we have? 9:10. Okay, so I think that's sufficient for today. So rather than start another lecture with the last 10 minutes left, I'm just going to call it stop there because we're going to switch into a completely different topic next. Right. So that's it for today. I'll see you, I guess, either tomorrow or, well, tomorrow, I guess, in the last